Hey there, welcome to this class 17B, where Wout and I, Jeroen, will tell you a bit more about the Joule-Thomson effect. But before we do that, we will talk about sort of the final complete method to compute any partial derivative, like we promised you in the previous class. So in the previous class, 17A, we handed you a couple of new tools. Again, lots of math, but useful math. And remember also that all this math, the purpose of it is to express thermodynamic quantities which are difficult to measure in terms of quantities that are easy to measure. And the new things that we learned about in the previous class are well, certain partial derivatives that are in fact equal to well-known and very well measurable coefficients like the thermal expansion coefficient or the isothermal compressibility. I could mention all of them here, but I suppose you can also read them for yourself and you will probably remember them from the previous class. So as a matter of fact, the tools that you just saw are in a way similar to the tool that you see here. It's being forged by a blacksmith using other tools. Uh, and in fact, we earlier on we saw other tools that we have used throughout, things like the thermodynamic energies and all these different relations between partial derivatives. And hopefully, this very skilled blacksmith, that's you, being able to use all these different tools that we have derived. So just to give a short recap of all these tools here, it's a slide we have also seen in previous classes. So this lists all the four thermodynamic energies and their total differential and the partial derivatives that you can derive from them. You've learned about Maxwell relations, which can be quite useful. And of course, there are the mathematical relations between partial derivatives, all the ways that we've learned to manipulate them. And in this class 17B, we will learn about a general method to derive any of the about 500 partial derivatives that exist in thermodynamics. And we will be looking at the so-called Joule-Thomson effect, which deals with temperature changes in a gas during adiabatic expansion or when gas is passed through a throttling device. Okay, so let's first look at the evaluation of unknown partial derivatives. So we'd like to find a systematic method that is generally applicable, in particular to find partial derivatives related to quantities that are difficult to measure. Now, let's see how this systematic evaluation can be done. Well, suppose you have a partial derivative, then the first step of the process is to move the energy. So if there is a U, an H, an A, or a G in the expression, then we have to move that up to the numerator using the reciprocal rule. The second step is then to eliminate the energy term using the differential for that specific energy. And we will see later on what that looks like in practice. Then we end up with an expression where we can recognize certain partial derivatives that turn out to be equal to things like the expansion coefficient or the compressibility. So we can simplify the relations, replace partial derivatives with these coefficients that are known or can otherwise be measured. And we will also frequently use things like the Maxwell relations for that. If we run into things like CV or alpha, the more difficult to measure coefficients, we can use these known relations to convert them to other coefficients that are easily measured, like, for example, the Nernst-Lindemann or Meyer relation shown here. And note that all these steps that are listed here, they're not necessarily, they don't have to be taken necessarily each time when you do such an exercise. Sometimes you can skip some steps. Sometimes things are simpler than you expect. So all this deals with the contents of the watt reader in chapter 8. And what we will do in this class is we will guide you through an example, including all the Jacobian stuff that's mentioned in the watt reader. And let's say something about this Jacobian. It's a tool from calculus that can help you in the change of variables when you perform an integration. If you want to convert one differential dx1 to another differential dx2, well, this conversion can be done, but you need some conversion factor, and that's in fact taken into account by the Jacobian. And well, we are now thinking about partial derivatives in thermodynamics, and we want to change differentials and derivatives. And that's why this Jacobian is also of use here. And what I really would like to emphasize that in this class, we don't really need to understand what the purpose is of the Jacobian or how it's derived. The only thing we need to know is a little bit about how it works. And that's what we will show here. And if you want to know more about the Jacobian, you can refer to your calculus course or to the Wikipedia page. So what is this Jacobian? Well, it's a matrix, and it's a matrix that has matrix elements that are partial derivatives. It's a matrix of partial derivatives, and it can also be written in this particular form here with this notation. And now let's take a closer look at how this matrix is actually built up. And let's try to remember this for a later slide. So you see that this stuff here in the numerator, we have on the first row, we have the F1s, and then each row, when we step down a row, this index increases. So we go from 1 to m in the downward, in the vertical direction. Whereas the x variables, x1 until xn, they are enumerated in the horizontal direction. So let's keep this in mind. What's here in the numerator is built up in the vertical direction, and what's in the denominator is built up in the horizontal direction. Now, often we want to take the determinant of the Jacobian matrix, and you will probably know that the determinant of a matrix, for example, a 2x2 matrix with matrix elements A, B, C, and D, is simply calculated as the sum of these two products, AD minus BC, sort of a cross product, and then you take the difference. So let's see if we can apply this procedure to a certain partial derivative, and we will take the same partial derivative that's also used in chapter 8 of the watt reader. So we're talking about dHdP for fixed temperature T. Well, the first step is to move the energy in the expression to the numerator, and that's already the case. So we don't need to apply this reciprocal rule. This step we have already taken. Great. Now we're going to try to eliminate the energy using the total differential for the energy in question. And this is something we can look up. We can look up the total differential for the enthalpy, which is this expression T ds plus P dP. You've seen that many times before. And of course, this expression formally contains partial derivatives. this partial derivative here is equal to t, and this partial derivative here is equal to v. Okay, they contain the enthalpy, but it's not really the thing that we're looking for, because we have this particular partial derivative, which is almost the same as this guy, but a different variables is held constant. So what can we do about this? Now the water reader employs some Jacobian magic to derive that this expression here, the one that we're actually trying to rewrite in simpler, more easily measured terms, is equal to this whole expression here. And we will see later how this is actually derived. Now, why is it interesting to write this expression in this form? Well, you recognize that this this partial derivative here is the one that also shows up in the total differential for the energy, or for the enthalpy. And the same goes for this partial derivative here. So that makes life simpler. That will help us in eliminating the energy from the expression. And how does that help us? Well, this partial derivative, we know it's equal to t. And this partial derivative is equal to v. So indeed, we have eliminated the energy now from the expression. This is also an interesting partial derivative because it's equal to 1. That also makes life simpler. But we still haven't shown, or not understood perhaps, how this expression comes about. How can you derive from this expression this whole thing here? That involves Jacobians. Let's take a look at how that happens. Let's first start by showing that we can write a partial derivative actually in terms of the Jacobian determinant that's written in this way. So the determinant is expressed by these vertical bars, and this thing here is this notation for a Jacobian matrix that we have seen before. Remember when we were looking at this at the structure of this matrix. This expression has 3 variables, h, p, and t. And these variables also come back here in this expression for the Jacobian. We have the h here on top. We have the p here in the denominator, and this t that's held constant here, that shows up here on the right side in the 2 brackets. And we're going to use this to build up a matrix, of which we will then take the determinant. And now remember the way this matrix is built up. So we start, for example, in the top row with a partial derivative of h to p for constant t. That's the one we put here in the left top corner. And then going in the horizontal direction, we then need to take the partial derivative of h to t for constant p. That's the one here. And now we're going to move from h to t. So we have to go down 1 row. We go down in the vertical direction, and we take dt, dp. That's here. And then the last one is dt, dt for fixed p. This is now our Jacobian matrix, and we are taking the determinant of that. Remember that that's the expression that we want to use, and if we apply this, then this is the expression that we find, where we notice that dt dt is 1, and dt dp for fixed t is necessarily 0. This thing doesn't change. So this entire term is 0, and what we end up with is just this one here. And this is exactly what we started with. So here we have shown that indeed you can write a partial derivative in terms of a Jacobian determinant. Good. Now, why do we even bother doing this? Well, the reason is that we can apply the chain rule that we know from the partial derivatives math. We can apply this chain rule also to the Jacobian. And I'm not going to prove this here in much detail, but you can sort of it's not difficult to imagine that something that's so tightly related with partial derivatives obeys some of the same rules that single partial derivatives also obey. So it turns out that if you have a Jacobian written like this, you can use this chain rule and introduce a dummy variable, or actually a set of variables. And we want to use S and P here. We write that here in the denominator, and here we write it in the numerator, so that in our minds these cancel out, and then you have this one again. But in this way we create this product of two Jacobian matrices. And why do we choose to introduce S and P as a dummy variable here? Well, that's because the energy, the enthalpy in this case, is expressed as a function of S and P. And that's how we eventually find partial derivatives that are equal to the temperature, for example, so that the dependence on H drops out. So this is something we can do. And what is shown here is actually a matrix product, because this one is a Jacobian matrix. This is another Jacobian matrix that we could build up along the same lines as we have done here. And we know from matrix algebra, we know that the product, or that the determinant of a matrix product, is the same as the product of the two determinants. So we can write it also like this. And these things we can evaluate using this expression here. Now, I don't want to do that here in every detail, but using the cyclic rule, you can do this. It's reasonably straightforward to do this. Now, what does all this Jacobian magic bring us? Well, we can express this partial derivative in terms of this stuff here, which we saw actually a few slides ago. And we could show that this simplifies to this expression, because this equals the temperature, this partial derivative equals the volume, and this is 1. So that's a good step already in the right direction. But now we can do more. Now we're going to apply the Maxwell relations. We're going to apply the fourth Maxwell relation to convert this partial derivative into this one. And in this one, we recognize the thermal expansion coefficient beta. And when we insert this into the expression, then this partial derivative here turns out to be totally expressible in terms of quantities that can be easily measured. And for example, we could insert the thermal expansion coefficient for an ideal gas, which is 1 over T. Then it turns out that this partial derivative is 0. So that basically proves that for an ideal gas, the enthalpy does not depend on the pressure. It only depends on the temperature. Now here are a few slides that I want to go relatively quickly, but you can always stop the video and take a closer look if you like. Let's take a look at internal energy changes. So things, total differential du. Well, we know that we can express du in terms of partial derivatives to the temperature and the pressure. Now with our new tools, in sort of the same way that we saw on the last 3 slides or so, we can actually show that these partial derivatives are can be expressed in terms of, again, measurable coefficients or thermodynamic quantities. And we can do that for both of these partial derivatives here, and then we end up with this generally applicable expression for internal energy changes of basically any substance. And if we want to know, for example, changes of the internal energy of a substance when going from pressure 1 and temperature 1 to pressure 2 and temperature 2, and we can just integrate this expression here. And again, in this expression, all these quantities are either known or can be measured, so you can measure and determine the change of internal energy. And you can find similar expressions, similar to this one, for the other energies, for enthalpy and for the Helmholtz and Gibbs energies. So we can take a look at a few of these general expressions. We've seen the expression for du. There's also a general expression for dH, the changes in enthalpy, and even for the entropy, which, of course, well, we have said 1,000 times that this entropy is difficult to measure. But here we have an expression that relates changes in the entropy to changes in variables that can be measured, that can be determined. And again, we can integrate these expressions, if we like, between the appropriate integration limits and find the total changes. And it's this kind of expressions and their integrals that are used to make the tables and the diagrams that we have seen and used in block 4. So how does the internal energy, U, depend on the pressure and temperature for an ideal gas? So again, we have this general expression for internal energy changes as a function of pressure and temperature. For an ideal gas, we can express the specific volume as follows. And we can express the thermal expansion coefficient and the compressibility coefficient also in terms well, as 1 over T and as 1 over P in this case. And if we insert all this into the general relation, then it turns out that this du is simply CV dt. And this is basically a proof of what we already used before, that for an ideal gas, the internal energy is only a function of temperature and not of pressure. And similar arguments apply to enthalpy changes of an ideal gas. You can show a similar relationship. Now, what this basically says is that it says that U is only a function of the temperature. And looking at how CV is defined, it turns out that CV is only a function of temperature too for an ideal gas. And well, let's take a look at the variations of the internal energy for an incompressible substance. Again, the same expression that we can start out with. For an incompressible substance, we have that dV is 0, so whether you change the temperature or whether you change the pressure, the specific volume is not going to change, so these partial derivatives are 0, and these coefficients are 0 as well. We can plug that into the general expression, and it turns out that we have that the internal energy is, the change in internal energy is just Cp times dt. And from the Nernst-Lindemann equation, which tells us the difference between Cp and Cv, well, we can tell that this one here is also 0. We saw that during the previous class. So Cp is equal to Cv for an incompressible substance. We've seen that result before. We had figured it out by reasoning, but this is now the mathematical proof that this actually is the case. And together with what we saw on the previous slide, we find an important fact of thermodynamics. If you treat, for example, air as an ideal gas and water in a lake as an incompressible substance, then in that case, you can write the heat capacities as only a function of the temperature, and the same for the internal energy as well, for the air as well as for the water. For the water, in addition, you can write a single specific heat um, because Cp is equal to Cv in this case. Now let's switch gears a bit and talk about the Joule-Thomson effect, which is something that occurs in throttling processes. And these play an important role in thermodynamics. The throttling processes are at the heart of many thermal devices, such as refrigerators, air conditioners, heat pumps, and so on. Throttling is an irreversible process, so everywhere where it occurs, you have to take into account that there are additional losses there that will limit the performance of your device. And some examples that we have seen are a refrigerator. The snow cannon is also interesting. It's compressed air that is mixed with tiny water droplets, liquid water, and then it's expanded. And during the expansion, the air cools down, the water droplets freeze, and they form snowflakes. And now Wout will tell you a bit more about the Joule-Thomson effect and a thermodynamic property or quantity called the Joule-Thomson coefficient that's related to that.
Dear students, welcome to another video about thermodynamics and mathematical relations. And this one is about the Joule-Thomson effect. And this effect has to do everything with expansion. And actually it describes So the Joule-Thomson effect describes the adiabatic temperature changes due to the expansion of a gas. And actually we have met this effect before, but we haven't gone into detail. And the device which it is and it was applied is the throttling valve. And that looks like this. And yeah, this is the throttling valve, and there's a flow going in, and there's a flow going out, and it's always assumed to be adiabatic, so there's no energy transfer with the surroundings. And since the flow going in is equal to the flow going out, the enthalpy is constant. So there are no changes of enthalpy. But there are changes in temperature and pressure and velocity and whatever, so we're going into detail with them. Well, since you're all mechanical engineers, I made a schematic drawing of an example of a Joule-Thomson valve, and this one looks very much like the one you have at home at your tap for drinking water. There's a mechanism going up and down, and this mechanism determines the amount of flow that flows through this nozzle. And of course the flow coming from this side has a certain volume and certain pressure, a certain temperature, and when going through this narrow area, the velocity has to increase, since the mass flow, of course, should remain constant. So the flow, the properties of the flow they should remain constant, as can be derived, as was derived by our great hero Bernoulli. So it needs to obey these relations. And we're not going into detail into this relation, but keep in mind that these properties should remain equal. What we're actually interested in is in the change of temperature due to difference in pressure, because there will be difference in pressure, since this pressure needs to remain, or this needs to remain constant. Well, like I said, volume will increase, volume velocity will increase over here. So this pressure should change as well. So there will be differences in pressure. And Well, we can just have a quick experiment, a small experiment. If you blow to your hand with your mouth wide open, like this, you'll feel your hand gets warm. But if you blow onto your hand with your mouth like this, you will feel that your hand gets colder. So the velocity and the pressure have to do something with the temperature of the gas flowing through a nozzle. In this case, your mouth was actually the nozzle. So we are now interested in change in temperature with respect to the pressure for a constant enthalpy. And this is called mu Jt, and this is the Joule-Thomson coefficient. And well, to derive this, I'm going to use a couple of mathematical tricks, and they're all the constants I need are already written down here. And well, I'm going to derive this first to get an equation that gives something, some idea of the behavior of the Joule-Thomson coefficient. So let's dive into this. First thing I'm going to do is rewrite this equation. dt, dh, dp is pressure for constant enthalpy. And actually this will be equal to, and you can check it yourself, to dt, since h is in this equation, p and t are involved, dh for a constant pressure, because pressure isn't in this derivative, partial derivative, and enthalpy with respect to pressure and for a fixed temperature. I'm going to rewrite this one first. That's the easy one. dt, dh for constant p is actually, and I'll show that over here, the inverse of dh dt for a constant p. So from this it follows that dt dh for constant pressure is equal to 1 over Cp. And again, you can check this for yourself. So this is equal to 1 over Cp. Over here, this is a little more complicated, but I think you can still handle this. For this, I'm going to use this equation. So let me rewrite this part. So rewriting this, the dh is equal to, dh dp is equal to, and I have to divide everything by p, is equal to T multiplied by ds dp for a fixed temperature plus V. And so now I've just rewritten this equation into partial derivatives. Now I'm going to use this equation. It's the Ford-Maxwell relation. And I can rewrite this by applying this equation. So dh dp for fixed T is equal to the temperature multiplied by a minus sign, the partial derivative of volume with respect to temperature for a fixed pressure, plus the volume. So this gives me for a fixed pressure. And this is actually as far as we get. The most simple form of the Joule-Thomson coefficient. Okay, and actually for me it doesn't really say anything. Maybe if you're really into these derivatives, you can maybe solve it. But instead of doing the reasoning for all these coefficients, I'm going to do something different. I'm going to use experimental data, well-known experimental data. And from this experiment we know that the behavior of the temperature versus pressure for a constant enthalpy looks like this. And here as well. And these lines are all isentropic. So we've got the isentropic lines. Well, and if we take a close look into these lines, well, we can see that there's not such thing as a fixed dt, dp for a fixed h. It differs along the line. And for this, we're going to analyze it in different parts. And the first part I'm going to analyze is this part. So over here. And over here you can see that the slope increases. So dt, dp will be larger than 0. Well, here you can see that there's actually a local maximum. And this maximum over here, dp, dt, dp is equal to 0. Well, after maximum, so over here, dp or dt, dp smaller than 0. Okay, now we need to take care of the behavior of these things. Because what happens if dt, dp is smaller than 0? Well, let's assume if we're talking about a nozzle or a throttling valve, we always go from a high pressure to a low pressure. So there's always expansion going on. So let's assume we're going this way, then the behavior will look like this. I'm going this way, so from here to there, actually the temperature will increase. So actually temperature increases. Okay, so of course only increases when expanding for a fixed. Let's mention this for just to make everything complete. There's an h. So delta t of the partial derivative of temperature with respect to pressure for a fixed enthalpy will remain a constant temperature, and this is actually a very important temperature. But I'm going to tell you more about this later. And of course we have this other, the dt, dp for an increasing, well, with an increasing slope. So over here, if we decrease pressure, so expansion, temperature will decrease. So temperature decreases. Temperature decreases. So actually, and since we've got all of these lines, so at the for each isotop, we've got a series of temperatures and pressures that relate to each other. And actually, if I plot a line through a maxima value, it will more or less look like this. And this is what is called the inversion inversion point. So over there, the behavior of the gas will change from a gas that is cooling to a gas that is heating up. Yes, so pressure will decrease or increase. So this inversion point determines when it will happen. So this inversion point, actually it's a material property, so air has another inversion point compared to helium or to nitrogen. So it's a property of matter. And there's one, for instance, air, nitrogen, oxygen, all have a high inversion point, so higher than room temperature. So when expanding, they will be cooling. On the other hand, for instance, hydrogen, nitrogen, helium, they have a low inversion point, lower than room temperature. So when they're expanding, they will actually be heating up. So it all depends on the temperature. And every substance got its own inversion point curve, or inversion curve. And there's one I would like to show to you in particular, Larry. It's deodorant. And I'm going to show you that this has a very high inversion point. First, in this can, of course, there's compressed deodorant, compressed gas, and the main it consists of methane, propane, all gases to get the perfume to get it out. And it's at approximately 15 bars. It will expand to 1 bar. At 1 bar, the Joule-Thomson temperature, the inversion point is about 400 degrees. So I'm going to expand it now on my hand. You should see what happens. And you can directly see that it is liquefied and my hand feels really cold. So it really cools down. And this is the proof of the Joule-Thomson effect. This is all due to Van der Waals interactie. And Jeroen will explain this principle in the slides coming up now. Good luck and enjoy.
Thank you, Wout. Like Wout already mentioned, there is a couple of slides where we will explain how this temperature change in a gas comes about when it expands. This is not compulsory. The slides are fun and interesting to watch, I believe. But if you are in a great hurry, then you might fast forward to slide 27 and take a look at the slides 18 through 26 at a later time. Now, in the Joule-Thomson effect, we saw that some gases will cool down during expansion, while others heat up. Now, how is this possible? Well, there is a reason for it, and it has to do with the interaction between molecules or atoms, or the so-called interaction potential. And if we're talking about interactions between atoms or molecules, then we're talking almost by definition about a non-ideal gas, because for an ideal gas, we assume that there are no interactions between them. Now, please note that the following slides, the little bit of explanation and the animations that we're going to show are for illustration only, and they need not be known for the exam. Now, what does that interaction between atoms and molecules look like? What's happening there? Well, assume you have two atoms or molecules. It's the same story in the end. Let's assume you have two of these particles at a reasonably large distance, but not too large. In that case, there is what we call the Van der Waals attraction between them. And how does that work? Well, let's assume that we have two atoms sitting at a certain distance from each other, and an atom is built up from a positively charged core or nucleus, and it's surrounded by an electron cloud, which has a negative charge. Now we bring these two atoms close together, not too close, but something like shown in this graph here. And what happens now is that these electrons, when they look to this side, the first thing they meet is other electrons. And they have the same charge and they tend to repel each other. So the electrons are pushed away in this direction, but this nucleus that's positively charged, and the first thing it will see is these electrons here, and it likes opposite charges, so it moves that way. So the atom will deform a bit, like shown here, and this is a greatly exaggerated picture, but it is the mechanism that's going on. And the whole thing, well, the whole thing is symmetrical, so the other atom will do the same thing. And in the end, you will have two atoms with deformed charge distributions that form two dipoles. It's an electric dipole. It's a concept from electrostatics. And these two things, these electric dipoles, they will interact with each other. And now this is an example based on atoms, but the same thing will happen with molecules that are composed of multiple atoms. So this is what happens at a reasonably long distance. Atoms will and molecules, they will attract each other through this van der Waals attraction. Now, if I would bring them very close such that these electron clouds start to overlap, then quantum mechanics tells you that, well, the electron clouds don't like that and the atoms are pushed away. They are repelled. So when you bring them close together, there's a very strong, what we call electron cloud repulsion. And both of these interactions, they can be modeled, and one simple model is the so-called Lennard-Jones potential that's drawn here as a function of the distance between the two molecules. That's the potential energy between them. And the van der Waals attraction, that's the interaction between the two dipoles, that's modeled as a 1 over r to the 6 potential, because you can show, if using electrostatics, that two dipoles interact through a 1 over r to the 6 potential. And it's an attractive potential, which means it has to be negative. So that's why you put the minus sign here. And to this van der Waals potential, you add a repulsive potential, which corresponds to this electron cloud repulsion. This term is positive and it scales as 1 over r to the 12, which means that when r gets smaller and smaller, this thing diverges rapidly. That leads to this potential barrier or potential hill that's very steep. Now let's take a look at what the effect is of the Lennard-Jones potential on the kinematics of molecule-molecule collisions. So let's assume we have two molecules sitting a certain distance apart. I can also indicate that in the graph that also contains the interaction potential. We have one molecule sitting here at the origin. Its coordinates are fixed, and here's a molecule that will be moving, falling towards molecule 1. And you can think of this plot as the potential seen by molecule 2 with distance coordinates relative to the position of molecule 1. Whereas here you will see the same molecules, molecule 1 and molecule 2, but they start falling towards each other in a symmetrical way. So we will run a simulation, and the simulation will start by giving the molecules a initial velocity. And the two velocities, they add up to a total initial kinetic energy indicated by this horizontal line. And what you will see happen in this animation is that the molecule will start falling towards molecule 1. When they get close, this potential well actually leads to an attractive force, so they are accelerated towards each other. And then when they get close, the repulsion kicks in. The two molecules separate again, and when they roll up the potential hill, they slow down, and then they regain their original speeds, but in the opposite direction. So let's take a look at this animation. So here they approach, they accelerate, they bounce, they decelerate, and they separate again. So here you see sort of the effect of this Lennard-Jones potential on the collision. Now let's have a look at two different scenarios. One scenario is similar to what we saw on the previous slide. It's where the potential well depth is comparable to the kinetic energy, as can be seen in this graph. And then there's another scenario that we will consider. That's where the kinetic energy is much larger than the potential well depth. So then we have something like this. In this graph, we have the same kinetic energy, but here we have a different potential energy curve, which could correspond, for example, to atoms that have a much smaller van der Waals attraction. And this potential may look completely different, but if we would zoom in here, then we would still see a small dimple. But it's just that the van der Waals attraction is much smaller. You could also think of it as this potential here, but then the kinetic energy being much higher than shown here. That's an equivalent situation. So we're going to have a look at what collisions look like and how the kinetic energy behaves for these two different scenarios. Now let's take a look at the first scenario. That's where the potential well depth and the initial kinetic energy are comparable. And what we will do is we will simulate how three molecules move and interact while being placed in this cylindrical two-dimensional container. And I will be simulating their motion, and I will be plotting the instantaneous kinetic energy as a function of time. And after a while, we will very rapidly increase the size of this container. That's indicated by this vertical line here. And it's done so fast that there's actually no time for the container, the expanding container, to do any work on the molecules in the gas. So let's see what happens here. So when we look at the container and the molecules, you see that they bounce around, they interact, and they interact actually quite strongly. Sometimes they form small clusters. There's this slinging motion when they collide until the container expands, and then the number of collisions per second goes down very rapidly. In the meantime, we see this kinetic energy plot being updated in real time. And let's take another look at the same video. So it starts again. Here you see peaks. The kinetic energy quickly increases way above the original kinetic energy. And this has to do with collisions, because each time when there is a collision, the molecules, they rush down this potential well, and their velocity increases, so the kinetic energy increases until they bounce back, and then they still have a high velocity in this section. So collision here actually leads to a kinetic energy increase. Note also that the initial positions of the molecules at the start of the simulation was chosen such that there was no potential energy. I chose the distances actually such that the potential energy here is 0. So so I know exactly how much initial kinetic energy I stick in. That's given by this horizontal line. Now, what's the conclusion that we can draw from this simulation? Well, during the first section, there is this increase in kinetic energy because of the collisions. And the kinetic energy of the molecules in a gas, that's basically equivalent to the temperature of the gas. And after the expansion, because there are much less frequent collisions, the kinetic energy on average is smaller as well. And we will actually, this is an example of cooling, and it has to do with the van der Waals attraction. And if you let a container expand or a gas expand, the van der Waals attraction actually leads to the cooling of the gas. So this is one interesting scenario. Let's have a look at the other scenario, where the kinetic energy is much greater than the potential well depth. We still have the same container, we're going to do a similar simulation. We have the same kinetic energy. And this is the initial configuration that I was just talking about, the 3 molecules sitting in such a way that the potential energy is exactly 0. And the only thing that happens initially is they have velocities in a certain direction. So let's start the simulation again. And again, we see the molecules bounce, but there's no longer this interaction. There's no longer this slinging motion. In fact, each time they collide, there's a dip in the instantaneous kinetic energy. And that's because now they roll up this potential energy hill and they lose speed. So they lose kinetic energy during a collision. That's why you have these dips here. So initially, when the container was still small, the kinetic energy is actually lower than this horizontal line on average. And then after the expansion, these dips are much less frequent and the average kinetic energy is higher. So this is then an example of heating due to less frequent repulsive interactions. And the only thing that's different is the interaction potential relative to the kinetic energy. So these are 2 examples that hopefully give you some idea of how the interaction can lead sometimes to cooling during expansion and sometimes to heating. Now, just as a final proof that this is not just an artifact of my simulations, but actually some real physics that's going on, we're going to have again a look at scenario 1. But this time also consider the potential energy and the total energy. The total energy is the sum of the kinetic energy that we already saw. Of course, there's also the potential energy of the molecules. The whole system is isolated. There's no energy exchange with the surroundings. So from the first law of thermodynamics, we know that total energy should be conserved. And let's see what happens during the simulation. So this is again scenario 1, strongly interacting molecules. Blue is the kinetic energy, yellow is the potential energy, and green is the total energy. And this is what happens when we run the simulation. Turns out that each time that the kinetic energy increases, there's a corresponding decrease, the same size but opposite sign of the potential energy. And the sum of the 2 is this green line, which is perfectly flat. And it doesn't change. It's the same height, same level before and after the expansion. So the total energy is conserved, but you can tell that before expansion, there was more kinetic energy on average and less potential energy on average. And after the expansion, things change and the kinetic energy goes down. That's when we have our cooling. So hopefully you found this convincing and interesting, and we'll continue with the rest of the video lecture now. Okay, this is the end of this class 17B. Actually, we're now done with all the math, and in the next class, class 18, we will be looking at combustion engines and diesel and Otto cycles. We're looking forward to that. Now, these are the important formulas that we have shown at the end of each video lecture. Thank you again, Veni, for letting us use your slides. And this is then the very final slide with a couple of questions. Please take a minute to look at these questions and try to answer them. And if you have any questions, feel free to approach us. Okay, see you in the online session.